Okay, so good morning, everybody. Welcome to the second day of the summer school. So yesterday was all about DDA data analysis, and today will be the first day where you see the DIA capabilities of MaxQuant. And yeah, as you can see in the program, we will spend now 90 minutes on MaxDIA, and then after the coffee break, there will be another session by Hamid on actually how to use it, so tutorial on MaxDIA. Yeah, the rest of the day we'll have other interesting talks. So the highlight is, of course, Albert's keynote presentation that we are looking forward to, and that will be the day. So as you remember from yesterday, so these are the two main ways. So aside from targeted proteomics, how one can analyze or record shotgun proteomic data. So one is in the data dependent mode, and the other one is in the data independent mode. In the data dependent mode, so the MS1 data is the same between the two, and the MSMS data in the data dependent mode is, as the name says, depending on the data and tries to isolate, if possible, single molecular species, so in this case, single peptides for fragmentation. And you get this relatively more or less clean spectra that contain fragments of, if possible, only one peptide. And in the DIA mode, you don't try to isolate single peptides, but you have wide mass ranges in which you select ions for fragmentation. And so because of that, then also the spectra are more complex, contain ion fragments of usually many peptides simultaneously. And then it's actually more complex problem for the bioinformatics than to disentangle the spectra, deconvolute them, and assign the contributions of fragments to the precursors. So that's then a more difficult problem, which is kind of more or less trivial in the DDA mode. So in, yeah, I think now more than a year ago, we then came up with the DIA workflow within MaxQuant. So MaxDIA is not a separate software, but it's just a workflow within. So there's only one MaxQuant software, and it has this DIA workflow incorporated. And you will see then in practicals how exactly you would analyze data with MaxDIA. And so the idea is to have a comprehensive platform, just as we have it for DDA data, now also for DIA. And so at the moment, what is in terms of mass spectrometers that are supported, it's then all forms of Orbitrap, Bruker timsTOF Pro, and also SciEx machines are supported. And so the big advantage of having the DIA workflow incorporated in MaxQuant is that we can reuse many of the algorithms that were developed in the DDA context, but which are nevertheless applicable in many cases without any changes one-to-one to DIA data as well. And in some changes, some adaptations are needed to make it working with DIA data, but nevertheless, a lot of concepts can still be reused. So examples for this is, for example, nearly everything that happens on the protein level, like the protein FDR control or the grouping of the shotgun peptides into proteins. So all of this doesn't care about how your data was produced, if it was produced with DDA or with DIA methods. So this can be just one-to-one reused. And an example of adapted algorithm is the MaxLFQ algorithm that we saw yesterday evening, how it is working for DDA data. So this can be modified to work even better in the DIA data, because one can now make use of the fact that for each peptide you have many signals. You have the precursor signal and you have many fragment signals. And so this will give you more of these pairwise ratios that the median is taken off in the MaxDIA workflow. So in some sense, it's actually really made for DIA because you have more information that can be assembled into giving you a good estimate of the protein ratio. So I should say what I described in the beginning is the MaxDIA workflow as it was at the time of the publication. So that's like 1 year old or something like this. And in the meantime, we actually have many improvements, very significant improvements, and we will talk about that in the end, what that exactly is. So I think most notably, it's actually the processing speed. So MaxDIA tended to be a little bit slow depending on the data. So that's not the case anymore. So there's no real speed difference between DDA and DIA data analysis in MaxQuant. So it's also scalable to large data sets now. So we're testing 400, 500 samples, and that's absolutely doable with the new and improved DIA workflow. So I should say this is actually in the version that was released before the summer school, so version 2.14. So this is the one that has all the improvements. So I mean, saying that if you want to do DIA analysis with MaxQuant, use this version and not older versions, because it's really a quantum leap to what I described in the beginning. Other things are the site localization is now working for DIA data as well, and it's actually exactly the same algorithm as for DDA. So it's also using the Andromeda score. So the localization score for DIA data is based on the same Andromeda score as is used in the DDA search engine. And so you get for phosphoproteomics data analysis DIA, you get exactly what you are used to from the MaxQuant DDA world, basically, right? So without any adaptations, you can do exactly the same data analysis, go with the site table into Perseus and do what you are used to do. And sensitivity, so maybe also very important, sensitivity. So sensitivity has increased a lot. We will see benchmark with the latest version later. And so yeah, let's get a little bit into the algorithms as they were, and many of things, of course, haven't changed. So it's still absolutely valid as they were with the publication of MaxDIA. So yeah, so one important conceptual thing here is that as you have seen, we are doing this higher dimensional feature detection on the MS1 data. But in DDA, of course, not on the MSMS data, because the MSMS data is not continuous. So you cannot do feature detection in higher dimensions spanned by the retention time or by the ion mobility. But you can do this in DIA because, as you remember from, wrong direction. As you remember from this slide, so we have now fragmentation windows that are large and constant, and that means that your fragmentation data will also be continuous. So at least if you concentrate on the fragmentation data coming from one of these windows, so this will produce similar to what you see for MS1 here, also such a plane of data, of continuous data, in which you can do higher dimensional feature detection. And so here it's shown for the retention time, but the same is valid also for the ion mobility if you have it, right? So that means that, as you can see here, so what we did on the MS1 level in terms of feature detection, we can just do exactly the same way in all of these planes corresponding to fragmentation windows. And so that is very advantageous for two reasons. So one is that it removes noise, because if you now match from the library into the DIA spectra, we only look for these features, right? So we are not we're not picking up noise that was not that is not in one of these feature areas, and we do it with complete features. So either we pick up the complete feature or nothing, basically, right? So you can imagine that removes noise from the MSMS data. And also we have a bit better control over how to use the intensity of the fragments. because we know now what part of the raw data of the MSMS raw data is actually corresponding to one feature, right? And then we can make sure that we don't overinterpret the data, because we can say now, we can require now that this feature is used only once for interpreting a library spectrum, so that you don't overinterpret the data by assigning data that is really connected by a feature, but which you wouldn't know if you don't do feature detection, by assigning it to multiple library spectra, which might be similar, and but we get to this in more detail later. And yeah, so we do the feature detection on the fragments also for timsTOF data, or in principle everything that has ion mobility dimension, but at the moment it's support is there only for Bruker timsTOF Pro data. And so, for example, here you can see a case where you have two peptides which have very similar mass to charge ratio distribution, so very similar isotope patterns, and were not also resolved by retention time. But you can see in the ion mobility direction, you can actually resolve these two peptides and get separate signals for the identification and independent quantification of these two peptides, which would not have been possible in a machine that wouldn't have ion mobility, right? So here you can see the benefits of ion mobility in general, and then we do this four-dimensional feature detection there as well, which just leads to the same things as in the Orbitrap data, that you remove noise a lot, which might be more of an issue here actually, because TOF data tends to be a little bit more noisy. And we have control over how we assign the features to library spectra here also in a very good way. So the first thing we want to do in the DIA workflow is to calibrate the data. And so it might be miscalibrated in several ways. So it could be that your masses are shifted systematically, and that could be in a nonlinear way with a nonlinear function. I think we saw that in the DDA workflow, that this is happening frequently. Also, the retention times could be shifted against each other. We also saw that in the labor-free workflow already. And also, so if applicable, the same can be true for the ion mobility measurements. And so we have now established a new workflow for doing this recalibration from the peptides in the sample. So it's not relying on spike-in molecules, but so if the sample is sufficiently complex, just uses these peptides. And as you saw yesterday in the DDA world, this is done with the two searches principle. So you first make a actually called first search to just produce calibration points for doing the nonlinear recalibration. So these results are not used for identification and quantification results in the end, but only for calibration. And so that's a very easy principle, because you have a search engine and you can just run it multiple times, and that's it basically. So in DIA you don't really have a search engine, and so that's why this concept breaks down there. And what we took as a replacement is this so-called bootstrap DIA workflow, and this means that we that we do the matching from the library to the sample multiple times, and always with increasing stringency in terms of, for example, mass windows and so on. And actually, the first matching we do without any constraints, so just with an initial mass tolerance, which is usually 20 ppm, and actually no constraints on the retention time or ion mobility. And then based on this first matching, so that these are then our calibration points for as input for the next steps, we do first thing we do is a linear retention time recalibration. And so that's actually all we can do at this stage, because the matching data will be a bit noisy, because we haven't used strict mass tolerances and things like this. So, but we can do linear recalibration with the retention time. And based on this linearly recalibrated data, we can calculate new windows or the initial tolerance window for the retention time difference. So that this we apply then in the next round of matching to the data, which will be more stringent now because it's actually using the retention time. So you remove false positives by this. And now you can do the same things with other quantities. So for example, the precursor mass could be linearly calibrated, the fragment masses can be linearly calibrated, and so on. And now you have another round of matching with even more stringent criteria, and you and so on and so forth. You go on becoming more and more stringent in these matchings, and in the end, you have completely recalibrated samples in terms of mass, retention time, and ion mobility, and all with nonlinear functions. So here you can just see that, so this is the score, so we get into this later, that, so this is before with less stringent matching, this is more stringent matching. You can just see that you over proportionally remove more decoy hits than you remove target hits with becoming more stringent, which is exactly what you want to do. You want to reduce the false positive rate in your data. And here you can see the results of the bootstrap workflow. So very similar to the results in the two searches strategy in DDA. You see that before the matching, you have a nonlinear dependency of the mass error on the mass itself. And you also have a nonlinear dependency on the retention time. These are the precursors, but you have similar things happening for the fragment data. And you see after applying the bootstrap workflow that the systematic component of the error is gone, and you just have basically more or less normally distributed noise around zero. Yeah, here you see that the distribution of errors as a histogram is also centered to zero by the workflow, and that's also the width of the error distribution becomes much more narrow than it's without the bootstrap, applying the bootstrap workflow. And you also can see that the intensity error, the mass error does not depend on the intensity here, but this is just a consistency check in this case because this was Orbitrap data. And for Orbitrap data, the error never depends on the intensity to start with. But for TOF data, we would also, where error actually does depend on the mass, on the intensity, we also have an intensity-dependent recalibration in the workflow. Yeah, so here you can see how the nonlinear retention time alignment is working. So this is always working between the whole library and one sample, right? One sample at a time. You do retention time recalibration. And so this assumes that your library is already within itself retention time aligned, because if you don't do retention time alignment within the library, you will actually not be able to have very precise alignment to the sample also, right? So that's why when you produce the DDA library with MaxQuant, you have to make sure that it actually does the retention time alignment, and this you do by switching on matching between runs when you generate the library. So this is then indirectly implying that the retention times are aligned in the library. So don't forget that if you generate the library with MaxQuant, obviously in the DDA mode, then you have to switch on the matching between runs. Right, and then you can see here that the library is then retention time aligned to 4 DIA samples with different gradients, so from length 30 to length 2 hours. And after these samples with different gradients are aligned to the library, you can actually do you can even do MaxLFU quantification on these without any disturbances by having actually non-comparable data there. So you can see the technical reproducibility between samples with different gradients, and you see it's all with very high Pearson correlation between the protein LFQ intensities. So yeah, as yesterday, so please interrupt me anytime when there are questions, right? So the next thing is then, so how do we actually generate the library? So we just read the output. I think there's a question over there. We just read the output of the DDA MaxQuant, the generated library, and we use the peptides, evidence, and MSMS file from there. And this is just loaded into the DIA run. And so the first thing we do in the DIA workflow is to consolidate the library a bit, because this will be obviously redundant in terms of having multiple spectra per peptide there. And so they have to first be put together. Wasn't that a question? Yeah.
Hola, ahí está. I want to ask about the library. If the library should, like, if you do the library, you should use the same gradient time when you run the library versus your sample, or I can make a library any gradient time? How is it?
This can be completely different. Can be completely different gradient, and so you can have like a very large long gradient for library generation, and then very short gradients for the samples. No problem. Okay. That's probably also recommended, because you want the library to be much deeper than, or at least as deep as all of your samples that you're going to measure.
And one more question, very short. Can the DIA runs also have different gradient lengths?
Yeah,
themselves?
That's actually what I was showing on that's exactly what this slide is showing, because this is symbolizing the library, which is aligned to each other. And now you have here 4 DIA runs, so with 30 minutes, 60 minutes, 90 minutes, and 120-minute gradient. So that's absolutely possible.
Sorry, I thought they are DDA.
I mean, not that one should do this, but if that happens to be what you have, then you don't have to resign. You can just go ahead, basically. And so that's the MaxLFQ technical reproducibility that I was showing here, that's exactly from these samples with different gradients, right? And you see the reproducibility is very high in the quantification.
I also have a question. Is it then performed with IRT peptides, or how do you match the retention times again?
No, this is based, so you don't need to use any exogenous molecules or whatever. So this is just like endogenous peptides in the sample, basically. So that's more or less why we are doing this bootstrap workflow, right? Because all of this could be much easier if we would just rely on some spike-in molecules, right? So then this would not be necessary. So this is exactly allowing you to do all this nonlinear recalibration without taking care of it, basically. Just that the software does it without you having to spike in something. Okay, so since the library is very likely redundant, meaning for one peptide combination of peptide, sequence charge, and modification, you will have many versions of these in the library usually. So they first have to be collapsed, and that's what we do in this consolidation step, where we however, don't blindly collapse everything that has the same sequence charge and modification, but we first form these RT CCS clusters, so retention time collision cross-section clusters, because you can have the same peptide. So I don't say now always peptide charge modification, but that's what I mean. You can have the same peptide in more than one configurations. So you might have seen, for example, that the same peptide occurs twice along the retention time, so that can happen. And the same can happen with ion mobility, that you find multiple configurations of the same peptide. And these you exactly don't want to average, because as you can imagine, if you have the same peptide occurring at early retention time and at late retention time, if you would now average these two, you might get a nice average spectrum, but the retention time is completely nonsensical, because it would be some number in the middle of the two configurations, which has nothing to do with either of the two configurations, right? So then averaging these would be not a good idea. So that's why we first go to these clusters, of which you can have more than one per peptide charge modification state, basically, right? And only these are then averaged, and the results of this averaging are these so-called consolidated library spectra. And then from these, we take the top n fragments, so top n meaning top n by intensity, and that's what we want to find back in the sample when we match the library with the sample. And then, at least in the first round of matching, basically we have to go like through all retention times and then judge if this consolidated library spectrum can be found in the sample, for example, at this particular retention time. And if you have ion mobility, then you have to do this on this two-dimensional pixel grid spent by retention time and collision cross-section. So at each of these points, you have to query if the raw data here is actually reflecting the ions of the consolidated library spectrum. And you have to do this obviously for all library spectra, right? And then to judge if the library spectrum fits here or here, we have to calculate a score. And this is actually the first thing that is now done differently in the new max point version. So the old score was working like this, that so at the given retention time, we just look, do we find the precursor? So at the precursor mass, do we see a feature? So at the precursor mass of this library spectrum. And then also for all of the fragments in the library spectrum, do we see a feature in the particular plane for this isolation window? Do we find features that are overlapping with this retention time mass and maybe a collision cross-section value? And then, so it's not just counting yes, no, or 0, 1, but for each of the places where it matches a feature, we then add a number to the score, which reflects how far you are away from the apex of the peak. So apex, like in this direction, in the sample, how far is this matching point here away from the maximum of the peak, right? And so if you hit the maximum, you would add 1, like in this case, and if the hit is somewhere low in the tails, then we would add a considerably smaller number to this. And so we go to the details how this is working now later, but let me already mention it now. You saw in the bootstrap workflow, we do many rounds of this matching. And in the first round, we do it exactly like, we still do it exactly like this. But for all the other rounds, we use now a trained machine learning model to judge how good the match is. So we're using a support vector machine there. And so the result of this is then, again, a continuous score, with like the output of the support vector machine, which is replacing this simple score. So the simple score we still do in the first round of the bootstrap workflow. And in all the other steps, we train a new support vector machine based on the data of the previous round, right? And then we use the output of the support vector machine as a new score, right? And so this was actually the biggest change from the released version 1 year ago and the version that you have now. So this makes the biggest difference in terms of sensitivity of the bootstrap of the whole MaxDIA workflow. So that was an important change. And so we still do this here, which is called second scoring. So the purpose of this is to remove the redundancy of assignments. So you can see in the upper panel, two library spectra that are matched into a DIA sample. And what you can see here is that there are several features that are matched to both of these library spectra, or this consolidated library spectra, right? And this is something that you don't want to have, because this is leading to overinterpretation of your data. So you would actually now conclude that both the upper and the lower library spectrum have good evidence of fragments in the sample, but that's actually not the case, because you are using just the same fragment twice here. But since we have done this feature detection on the fragments, we are aware of this. So any other workflow that is not doing the feature detection wouldn't actually know that you're overinterpreting the data, right? And so, but we know, or we would know, and we can avoid it by doing the second scoring. So the second scoring is just taking now a subset of the results of the first scoring. So it's basically omitting points, so that to achieve that each feature is used only once. And so of course you cannot do this in some kind of exact way, but this is based on heuristics, and heuristics is very similar to the razor peptide idea. If you assign peptides to proteins, where you can also have multiple assignments of peptides to proteins, but then for quantification, we want to use each peptide only once in the whole data set. And that's why we use that as razor peptide principle. And here you can say we use the razor peak, fragment peak principle to make this assignment also unique from the fragments to the library spectrum. So the tricky thing about this is that if you do this wrong, if you do this wrong, then you won't notice this in target decoy search, because so the target decoy search is blind to this mistake, essentially because you're always reverting both of them simultaneously, so you don't see that one of these assignments is wrong, basically, right? So that's very dangerous. So because if you see then in the target decoy, even with external FDR, blah blah blah, kind of validation of your data, you would actually not pick this up. Right? Okay, so then let's have a closer look at how we now combine the score with other features into another layer of machine learning. So this is not the layer of machine learning I was mentioning before. This is now once the assignment is done for all library spectra. We want to do now something similar to what we did in DDA with the posterior error probability. Only difference is that we now do this with machine learning. And so basically we want to use on top of the score, which is already an output of another machine learning layer, we want to use other features of the match to again get some kind of next level score, which then is used for doing the false discovery rate calculations. And you can see here the features that go into the score. So we have a feature space that is about 100 dimensional. So you have these 25 features where you have one feature per match. And then you have these fragment features here that are repeated for each fragment that you assign to the library spectrum. And then we again treat this as a classification problem with the label, this is a targeted, this is a decoy hit, right? And it's absolutely necessary to do this in cross-validation, so not just one model, but because otherwise it just won't work, basically. I think you will hear more about this in later machine learning talks. Okay, then we tried then different algorithms for this classification problem. And so for example, we took XGBoost, random forest, AdaBoost, and neural net. So neural network is a fully connected multiple hidden layer deep learning neural network. And of course, we tried just use the raw score itself. And then we had 3 criteria. So one is the ROC curve, area under the curve of this the classification problem. The other one is now if you use so everything else being the same, and you just swap the machine learning algorithm in MaxQuant, what is the number of peptides and what is the number of protein groups that you get, depending on the machine learning algorithm. And so as you can see, in all 3 categories, it's actually XGBoost. That is the one that wins. So in terms of ROC curve, in terms of identified peptides, and in terms of identified protein groups. And yeah, raw scores always the worst. That's good. Random performance is even worse than that. That's also good. And so at least in our hands, it's actually not the deep learning neural networks that are good or that are best. Actually, they're even the worst in these 2 categories. So that's why we then hard code. So you cannot select the algorithm anymore in MaxQuant. So we hard code that it's always XGBoost that is used there. And you could still change the hyperparameters of it. But so we have some default values, and yeah, as we heard several times now, usually our default values are good. So you're usually not expected to change these. And it's actually also good that these are not tuned on every data from you. So what we do tune on every data is the model. Like the model parameters, they are always calculated on the data that you're using, but not the hyperparameters of the model. So they are not tuned anymore, which is good for avoiding overfitting. So you won't get overfitting. First of all, this is all done in cross-validation. And then also we are not tuning the hyperparameters anymore based on new data. Yeah, so here, fortunately, XGBoost also puts out the importance of the feature. So there's a so-called gain parameter that tells you how important the feature was. And so actually, the most important feature was not the score, but it was the fact if the precursor has an isotope pattern or not. So that was at least in the, so this is still with the old score. And there actually the score was only the second most important parameter. So it will be interesting to see how this changed now with having the dynamic scoring. So now actually the score itself might be the most important feature, but we don't know. So actually, because the results are relatively fresh and new, that we don't know many of the details yet. So we just know it's doing something really good. So there are other interesting parameters that that are important for the decision. So one very interesting is, for example, the what we call sample fragment overlap. And so this is telling you if and how much the Y and B ion series are overlapping, right? So you know that the spectral identifications where you have Y ions on one side and B ions on the other side, and they never see each other, that they are not really good, right? Because you have a lot of flexibility in putting as many amino acids as you like in the middle between the Y and B series at the beginning and end, basically, right? In particular, this is even worse in DIA, because in DIA you don't have this fixed role between the precursor and the fragments, which kind of in DDA you get it naturally by selecting the precursor for fragmentation, and this you don't have in DIA. So here you actually have to be super careful that you assign the correct precursor to your fragments in the data. And if not, then you might actually get a completely different peptide identified. I think that's also not really caught in target decoy. I would think not actually, which is similar at the end, but it's completely different in the middle, right? So that can easily happen in DIA if you're not careful about assigning the precursor. And you can put also all kinds of crazy modifications, SNPs, some, what did we say, heterodimer, heteroenmer, ubiquitin, sumo chain. You can put all kinds of things in the middle if you don't have the Y and B series overlapping. And so also, fortunately, XGBoost told us that this is an important feature which made it into the top 10 ranking of the features. So then let's look at an old benchmark. So this was the benchmark when MaxDIA came out. And at this time, we were comparing to the Spectronaut versions that were out at the time, basically, so 13 and 14. So they also have newer versions by now. And at the time, yeah, we were very happy to declare that we have exactly this, or more or less the same performance as Spectronaut. So we didn't know what was coming, so we were very happy about this and declared victory or whatever. And so it was good at the time, but you know, time passes, world changes. So let's say we kept up with the challenges. So, but we will get to this later. So first, let's go through another important question here. So this is the question of missing values in DIA. So actually one of the reasons why one promotes the DIA is that it's supposed to have less missing values. So it's not true that it has no missing values, because every technology has a dynamic range limit, and so does DIA. And so it also has missing values. But you can actually control the extent of missing values by adjusting your algorithm accordingly. So there are two extremes that you could do here. So you could do like a quantification only workflow, so which doesn't care about if your peptide is identified in a particular sample and quantifies always, which is prone to, of course, quantifying noise a lot. But you would have, this is essentially what people mean if they say DIA has no missing values. But you can also do it in the other extreme, where you say, no, but before I do quantification of a certain peptide in a certain sample, I want to make sure that this peptide is identified in the sample with FDR threshold of 1%, for example, right? And so then this is the other extreme. That's a little bit like the missing value problem in DDA, because, I mean, there you exactly do it like this, that you have to have an MSMS spectrum in the sample that identifies the peptide with the set FDR thresholds, unless you use tricks like match between runs or something like this, right? So match between runs is basically not present in the DIA workflow. So this is replaced by this so-called transfer Q value. So the transfer Q value is an important parameter in MaxDIA, which now controls where you are between these two extremes. So the quantification only extreme or the almost DDA-like extreme. And now, depending on what you want from your sample, you can now dial yourself in any position between the two. So again, we have a default value where we think it kind of works. And but surely, I mean, if you want to play around with something, then this is certainly some kind of thing with an interesting handle on the data analysis, which you might want to try out. So then the quantification precision on replicates. So that's so actually we didn't even get to that now in the new version, but so this is what it was in the old version, and so that was considerably better than Spectronaut at the time. Also, like the pairwise correlations between technical replicates. So this is a data set with 27 technical replicates. And you see like color-coded the Pearson correlation for Spectronaut and MaxDIA between all of the pairwise combinations in the data set. And you see that we have not on average, but everywhere actually much higher Pearson correlation between replicates than Spectronaut. So then we looked at the comparison of the intensity output between Spectronaut and MaxDIA. So for MaxDIA, it's then IBEC, because this is some kind of absolute quantification that we want to compare between the softwares and the Spectronaut output. And we average these over these 27 replicates. And you can see actually the Pearson correlation is also not that bad across software. So you almost reach 0.9 Pearson correlation if we compare our IBAC intensities with the spectral node intensities. Right, and then of course it's not easy to say, okay, is any of them correct, or if yes, then which one of them is correct. But anyway, they're very close. But then we looked at IBAC or spectral intensity against RPKM from like transcriptomics of the same cell lines, and so in both of, so it's not really strongly discriminating or favoring one. So in both of them, we get this typical absolute quantification correlation coefficient of around 0.5 that you essentially always get if you do absolute quantification of transcriptome and proteome. It's almost context independent that this correlation is always in this area. So it's not saying that much really, but you would get the same results no matter if you use spectral node or if you use MaxQuant. Okay, so then we did this famous test of the accuracy of the FDR estimates, where we so we have an internal FDR estimate that is based on target decoy search, reverting sequences, and so on and so forth, basically, right? And then we compare this with, so that's what we call here internal FDR. So we compare this with the external FDR, which is determined by offering on top of the correct library also an incorrect library. So in this case, this was human cell lines again, and the correct libraries, of course, and also the one from human cell line from the same actually. And the incorrect one is we took another species and we took maize as the other species. It's actually old data from the first spectral node paper. So we're just reusing this here. And then we see that so these curves are now like the coverage in terms of protein groups, peptides, and PSMs as a function of FDR that we apply to the data. And you see that what you see is that the dashed and solid lines are agreeing very well. So this is just saying that the external FDR is agreeing very well with the internal FDR. So it's just a cross check if we didn't do anything wrong in the internal FDR calculation. So it's actually something that's a bit funny, and I don't understand that in the Diane workflow they're actually disagreeing a lot, and then they say, yeah, this is because we are conservative, so we're actually even much better than expected. But so maybe somebody can explain it to me. I think they should be the same. So if they're not the same, no matter which direction, something is actually wrong. But maybe I don't understand it. So then, so that's good. So that means our FDR estimates are correct with some caveats. So as I was mentioning, for example, this overinterpretation by using fragments twice and 3 times. So this you would actually not see here. But I mean, for those things that we are aware of that could go wrong, we took precautions that they don't go wrong, basically. Going over what you can see in the external FDR benchmark. So this was the benchmark for using the same library sample as the FDIA samples. So that's working very well. So then we went to another situation where we are using a completely different library than we have samples. And so the most extreme you could do is actually take the whole in silico proteome, like you take all the UniProt sequences, including the automatically annotated and splice variants, so basically everything you can get. And then you make in silico digest to tryptic peptides and peptides with 1 miscleavage. And then we did spectral prediction with our deep learning algorithm here that you will hear more about later. And so we have a huge, really huge library with all human tryptic and miscleaved peptides. And so this we are then using as a library. And the results you see on the right side. So again, also here, the internal and the external FDR estimates are agreeing very well, which tells us that basically that one is allowed to use a library that has nothing to do with the sample, which is also, of course, exactly what you want, because that means you can use a universal library. You don't have to measure a library again and again for new projects. You don't need sample-specific libraries anymore. So then, as I was already mentioning, we adapted the MaxLFQ algorithm to the DIA context. And so the main difference here is that, as I was mentioning already, that for each peptide charge modification state, you now have not only one signal, like the precursor intensity in DDA, but you have many sample intensities. You still have the precursor, but you also have several fragment intensities, for which you can now build pairwise ratios. And these are always, these ratios are always taken on same fragments or precursors. So for example, we have a Y5 ratio that first checks if in the two samples where you are, if you have the Y5 in both, if that is the case, a ratio is formed for the Y5. You do the same for the precursor, you do the same for all the other annotated fragments, right? And then you have on the order of 10 ratios, and they all, with the ratios from all the other peptides of a protein, go together, and you calculate the median of these for getting the protein ratio. Yeah, so then here you see coefficient of variation comparison. Then we see that already. But again, with the old Spectronaut, so that which was very good at the time, almost twice as good basically, and that's still good. So then we did some other benchmarks. So for example, here now we played around with different sizes of libraries, and actually also either having single shot DIA samples or fractionated DIA samples. So that's also something you can do with MaxQuant, that you actually fractionate your proteomic sample on the DIA side, and you can still get good quantification with the MaxLFQ algorithm, or you could also do for phosphoproteomics. You could still do fractionation on your DIA side, basically, right? And you get good quantification now. So here you just see example how this was working. So this was actually fractionated boxcar DIA and using the discovery library, and you see you get very good correlation again between samples in terms of Pearson correlation. So just to describe what we did here, so we had a single shot library, we had the deep fractionated measured library, and we had the discovered library. And if you now look at the fractionated DIA samples, you see that you gain a lot, of course, from when going from the single shot to the fractionated library in terms of protein groups, but you're still gaining when you use the discovery library instead of the deep fractionated measured library. So again, that's arguing for we don't need to measure libraries necessary anymore, at least for this kind of data, for Orbitrap data. That might still be a question that needs to be evaluated independently for timsTOF Pro data. So that it might be the conclusion might be different there, but surely for Orbitrap data, it's usually not necessary to measure a library. Yeah, so here, that's an interesting comparison with the three library approaches and the corresponding RNA-seq data. So that was, again, human cell line data here. And so if you look at the right side, the histogram, what you see as the gray histogram behind all of the others, this is basically what we get with RNA-seq for these cell lines. And this is binned into intensity, absolute quantification bin. So we just see RPKM of the cell lines. And now we sort what we get with the different library approaches on the proteomics side into these RPKM bins as well, right? So it's not by proteomics bins, but by transcriptomics bins. And then you see with what is common between all of the approaches is something that is biased toward high intensity. So this purple histogram, that's what all the approaches are getting. So you get everything at high and medium abundance, but you lose at low abundance. And then, but you get the most of the remaining RNA-seq histogram, either with or with both, actually, with the measured deep fractionated library or with the discovery library. And then with the discovery library, you get the most on top uniquely with the discovery library. So it's really the best option in this case. And what's also interesting, so we didn't filter the transcriptomic data by RPKM larger than 1 or log larger than 0. So that's why you have this this almost bimodal, or not almost, this bimodal distribution for the transcriptomic data. But what is actually good to see is that from this left mode, almost nothing is actually identified by the proteome, and that's actually how it should be, because so this left mode you would actually usually not consider in transcriptomic analysis, because it's things that are not believed to be resulting in a protein. So either because they're non-existent and just some statistical fantasy, or because they would correspond to very labile, or probably not the transcript, or maybe even the transcript is labile, but at least the resulting translated protein would not have a big chance to really exist for a long time. So it's actually a good thing. So that's another check of the correctness of the algorithm, that we don't get proteins here in this area. So that's a good thing. So then, yeah, here we just redid another project that was done with the deep fractionated library, even with sample-specific library here on FFPE tissue cancer samples. And yeah, long story short, so if you do the in silico predicted library, the discovery library with MaxDIA, you get higher numbers of proteins here, and you get even slightly better separation in the first principal components. So this discovery library that I showed to you, so this was produced with DeepMass, which is our recurrent neural network predictor for fragmentation libraries. So you will hear much more about this in Shamil's talk late this week, I think tomorrow or today, later at least. Hasn't happened yet. So so now it's also interesting that to see do the results depend on which algorithm you are using for predicting these libraries. And so first of all, I want to say there are different kinds of these predictors. So one is so probably the most popular at the moment, and also probably the most accurate in terms of correlation between predicted and experimental spectra. So these are based on recurrent, like bidirectional recurrent neural networks, and they train on huge data sets, like what you can download from Pride, or what Kista can synthesize in Weinstefan. And so they are very good, no doubt about this. Right? But then there are alternatives to this. So one is, so which don't use deep learning, or deep learning in a very simple form. So one is, so that's that has been pioneered by Leonard Martin's lab, where you say, okay, we don't, actually the problem why one needs these things is that you have, that peptides have different lengths, basically, right? So that's why you need this recurrent neural network kind of structure to accommodate variable length input, which is non-trivial for machine learning. So then, yeah, so here they said, okay, let's simplify the thing by just considering one length at a time. So I make a model for length 7 peptide, and I make another model for length 8 peptide, length 9, and so on and so forth. And then each of them is just a fixed length representation to start with. And you can use any machine learning you like, basically, to do regression on these. And so then you could, for example, just use a simple, fully connected neural network here, or they used random forests, I believe. And the third way of doing it, so that's also something we did in the same paper, is a window-based approach. So here you say, okay, I simplify the problem by predicting something much more simple, which is you go to one peak at a time, or you actually take the corresponding Y and B peaks at the same time, and you only want to predict how far below the base peak of the spectrum is this particular peak. And the nice thing there is now you can use a different feature space which is centered around the peptide bond whose breakage is producing these two peaks. You don't need the whole spectrum, basically, right? So this is a window approach, because you're putting like a sequence window around each bond, and then you move it by one, and so on and so forth. And yeah, so that's what we call this winner. So the NN means this is still a neural network here, but by now this is also replaced by XGBoost. So you see the trend, we're just replacing everything by XGBoost. So not so much because we have a hammer and everything looks like nails, but because it's really surprisingly well performing in a large variety of machine learning projects. So then how does it compare now if we use different prediction algorithms for predicting these spectral libraries, these in silico spectral libraries? And what we can see is that at least if you use like some of the good algorithms, the results are not changing much. So the gene count is actually more or less the same if you use deep mass prism, if you use ProSet, or if you use winner. And same is true for the peptides. So you see the unique numbers are actually very small compared to the peptides that are in common between all three methods. So that means it doesn't matter. Essentially, it doesn't matter. Although we know that winner, in terms of correlation coefficient between library or between true and predicted spectra, is a bit worse than the deep learning methods. We can see that although that is the case, undoubtedly, we can see that the actual DIA performance. So if you apply any of these in the DIA workflow, is actually not changing much, right? And this is actually very good news because that means that we can just pick the simplest. So we can just pick the non-deep learning model, which apparently, at least in this in silico prediction context, doesn't really have a major or any disadvantage. But it actually has many advantages because it's very fast. It's much faster than deep learning. And also, usually you don't need that big training data. So deep learning is, it's very precise and accurate, but like the deep learning paradigm is always asking for infinite data, essentially, right? So it's like coming out of the kind of Google search engine world, where basically you have all kinds of, the amount of data is no problem, but it's all a little bit noisy, unstructured, and then you have to find patterns and these super huge data sets, which is an advantage because you don't have to think about it. Basically, this is now your new brain, and you can switch off your old brain. Basically, is the idea there. And but that, of course, also has disadvantages. If you switch off your own brain, that also comes with disadvantages. And the biggest one is that you always need big data, like 1 million or 2 million examples or something like this. And with that comes computational costs. So that also means that they're usually very expensive in terms of training the model. And so actually for proteomics, that's a bad thing because so what they might be very good at is like this kind of vanilla flavor of peptides, right? So nothing special about it, lots of data and pride, or Krista has done a lot. And so on this, you can build these models. But if you now are in a special situation, let's say you have special modification, special mass spec hardware, other fragmentation techniques. So if anything is already a little bit different than what the mainstream is doing, you have a problem, right? Because that's not where the machine learning model was working on. And so there is, of course, transfer learning to help a little bit. But what I think is actually even better, I mean, if there are no disadvantages for the simple model, then just take the simple model. And you can just retrain it on any small data sets that you produce in your lab. And so we will see that. So we will provide actually a web server for doing this, exactly this. This is all coming later. And so this will also be, so this is not reliant on doing this on a web server remotely, but you can also do this yourself you can install it on your site and build your spectral libraries then with exactly the data that you are producing. which you can see here already, but this is coming. And so I want to spend the remaining time, of course, with questions, but also saying again, what is now new in 214? So 214 is the one that just came out with the summer school. So I think, so there are three very important novelties and actually many changes, right? So actually the whole peak detection changed, all kinds of parameters were tuned, so many things were changing. But like the three most important things is first of all speed improvement. So MaxDIA was admittedly a little bit on the slow side with the first release, and this is absolutely not the case anymore. So this is fast as it can be, basically. And we have now included the localization score for PTMs. So you get a side table now for DIA data, just as you're used to for DDA data, and you have the same localization score based on the Andromeda score. So not on the DIA score, but on the Andromeda score. Also for DIA now. And then, yeah, last but not least is the sensitivity increase, in particular for timsTOF Pro data. And this happened because we added 2 new levels of machine learning, and the third one is just coming also. So let me just summarize what this is again. So now in the version, we have 3 levels of machine learning. The first one is the one that we discussed in length, which is the rescoring the library to sample matches. So that was this 100-dimensional feature space that we saw, and this is using XGBoost. And the most important improvement is actually this dynamic scoring, which is done with a support techno machine at the moment. And so the purpose of this is, or the problem with this one here is that, so this one here can only improve things that it sees. So it's a little bit the same situation with the machine learning improved score in DDA. So most often you just rescore the top hits of the first level and not all of the sub-leading hits, basically, right? And because of that, if you made, like in the first scoring, a mistake that you took the wrong solution as the top scoring, and let's say the second top scoring is actually the true solution, you will not get the correct answer with the best machine learning in the world if you don't reorder these, or if you don't rescore all of the possible solutions. And this is very analogous here. So that's what the dynamic scoring is for. So the dynamic scoring is a little bit simpler in feature space. So it actually has only these illusion profiles that are matching, basically. But basically, it can make a very good comparison of all of them along the retention time or along the CCS value in one sample, right? So this basically ensures that you get the correct solution for a certain library hit in a certain sample, so that you don't already start with the second best solution, which you cannot save anymore with later levels of machine learning. So that's what this is good for. The purpose of this is that for one library spectrum, matching into one DIA sample, that you find the best solution in this. So never mind about comparing data comparison against other samples or something like this. So it should find the best one within this sample. And this then goes into the library to sample matches, XGBoost, basically. Right? So that's the purpose of this. And this made an enormous difference. So now we get actually many more correct hits with 1% FDR. And the third level, so that's still a little bit in exploration, is trying to find out per feature if this is a valid feature or not. So basically trying to find noise features and discarding them, or maybe not discarding, but at least scoring them and giving information to the other machine learning layers that this is not a good feature, basically, right? Which is currently also done with XGBoost, but this is actually not in the release now. So this is still being tuned. And also the others. So we're just in the process of tuning the machine learning. So this is also going to be improved or expected to be improved in the next release. And the next release will be in the first of the next month, basically, right? And the next to next release will be again in the first of the next to next month, actually. So next release should be even better. DIA, like in terms of sensitivity, should be even better. But already now, I think it's really, really surprised. We are surprised how good it is actually. And just to show you some recent benchmarks. So here we compare to. So there was a recent benchmark paper by the Diane guys. Running, so these are short gradients with Evosep columns, and then they were using 3 different gradients, like very short, medium, and long. But long already means very short, so it's like extremely short. It's like yeah, some kind of new Starbucks classification of size, I guess. So extremely small, medium, small, and small, basically, right? So. So what you can see actually on the extremely small, we even get a few more. We get a few more proteins than with the published Diane analysis. So these are protein groups, obviously. And on the other 2, we are very close, but yeah, a little bit less. But as I said, we are still in the tuning process. So that looks all very promising, I must say. That was also my last slide. And I think there is time for some questions before we move on with Hamid.
Thanks a lot. I have a few short questions. So one of them is that I remember with MaxDIA, the first version, we had to use a library if we wanted to like use a whole FASTA file from human proteome. We had to use the libraries from MaxQuant in a website.
Yeah.
Can we now use it like directly download it from UniProt and use it, or should we still use those?
Yeah, you should still use those because the FASTA file really has to correspond exactly to what was used in the library. So you still have to use those. I mean, that's also something that we want to make more comfortable in the future, especially if you now go to Xmas instead of deep mass prediction. Then we can just do them on the fly. So you don't need to, in future versions, you won't even need to download the in silico library anymore because it will just be generated.
Okay, great. And if we use it for PDM analysis, can we later download the library as a spectral library that is produced by MaxQuant and use it again later? Because then the library production itself takes a very long time.
Do you mean the library from...
If you use it for like you have a phosphoproteome.
But you mean to export the library from the DIA data with the DIA information?
Exactly.
No, that's also coming. So that's not there yet. So.
Okay. Okay.
And also just to that, so phosphoproteomics, I would now always do it with a library. So not in silico. So that's also something we're working on, but this is a bit impractical to produce the whole phospho library as like one thing. So this is much better to do this on the fly as well, right? But that's something we're working on. So library pre-mode for phospho will also come, but at the moment it's highly recommended to do measured library-based approach for phosphoproteomics.
Okay. And is it possible to use the libraries created by other like Diane or Spectrana and like use them as a spectral library in MaxQuant?
Yeah, I think to some extent, yes. So we have one import mode, I think, which is based on the Spectronaut format, where you don't have like, it's not whole peptides, but it's like transitions. It's that is in the list. So this we have. Let's say it's not super well tested because internally we never use it. We always obviously use the MaxQuant libraries. And so for Diane, I'm not sure if they can read the Spectronaut format, then we can read as well. I'm not sure if they have a format for themselves. So.
They produce a dot-slip. I don't know exactly if they can get Spectronaut libraries.
This I don't
know either.
Maybe somebody knows. I don't know.
And one more question, do you recommend then turning match between runs on when you do the DIA analysis?
No, in the DIA analysis, it has no effect because this is something that is only there for DDA.
Okay,
So
okay, doesn't work. A very last question. I remember the MaxDIA was taking all the threads of the PC when we were using it. Like we put the thread as 4, but it was using all the cores. Is this problem solved?
I think mostly yes. So the thing is, this might. I think this is something that yeah, it's not really something that is happening in Max Quant, but it's something that happens on the Intel or AMD side. I think so. Some of the processors are actually very good at now at using kind of 2 logical cores for 1 thread. So they're doing a lot of optimization on the chip, you know, to put the data exactly in place that they're actually using 2 cores. So it's actually not something we do, but it's something that Intel does. So and it's not always, so it's not very predictable because like the data flow into the algorithm has to be of a certain kind that the processor can do this. So that's why sometimes, let's say you have 12 logical cores and you set in Max Quant, you set it to 6 threads. So it can even happen that you see all 12 of them running. And that's not a mistake. That's just how good the chip industry is now.
But it doesn't happen normal DDA and so on. It just
yeah,
happens.
but it happens there also, but not
Okay.
so often. Like in the search engine, for example, it happens sometimes. And so it's unfortunately, it's not predictable which algorithm exactly is doing this, but it's more a generic thing, and it might be happening more. You see it more in DIA because so far you had so much time to look at the processors running, which is not the case anymore, basically. And I think you just see it more often there.
Okay, great. Thank you very much.
I thank you. So does MaxDIA, or have you ever tried searching using gas phase fractionated library, where you use like a sample and repeatedly measure over different mass charge ratios, and how will they compare to, for example, in silico generated libraries or highly specific libraries?
Actually, no, we haven't done. So good point, should be done, but so far we haven't.
Yeah, and the another question is, how does search, maybe too specific, but how does search time compares when you do, for example, using a predicted in silico library, or like a library generated using high pH fractionation? So in my experience, when using different software, using predicted library generally generates more IDs, but it's also the search time is considerably longer. So
yeah, that's still the case here. Well, search time depends on the library size, probably linearly in most places, and I think that should be linear increase. And also the memory usage goes up a little bit. So that I think that's the same with MaxDIA, that it takes longer the larger the library is.
thank you.
Hello, thank you. I would like to ask, is it possible when using an in silico library to not put any specific levers, like not any triptych, and do a specific search?
Yeah, this might be a bit too much. Then you generate a very big library. And so it's relating to the previous question that the running time scales linearly. Probably in this case, a bigger problem is the memory usage, which also scales linearly there. So I think for unspecific cleavage, HLA peptides, all these things, proteogenomics, it's the DDA, and that is the way to go.
Thank you very much.
Thank you, Jürgen. So in the MaxDIA world, the retention time alignment that we used to experience in the DDA world is completely different, right? So if you're using a discovery library, which has been created in silico, to compare it to now your LCMS runs,
Yeah.
there is no such thing as matching retention time. What you do is you create a kind of a curve from the experimental data matches. Is that how it works?
Yeah, so what we do now within silico is there is actually one, so there's one predicted retention time given there, which might not be the correct one, because this is like what we start with in every run, so it cannot be correct in every situation, but some very common kind of column is there then used for predicted retention times. And based on that, it would then actually do nonlinear recalibration of the retention time. So the only thing it cannot really do is if the retention order changes significantly. So this is not something that we can do then, basically in the predicted library approach. But everything that is more or less the same order, but just you know, it's the exact path is a bit different. So this will be properly aligned.
It's a good thing, I think, that we have that freedom now.
Yeah, and so this will also, I mean, this will also be, so once we go to this simple predictors without deep learning that can be just trained on your data, then you could just also make a retention predictor trained on your data, and then it will be, then it can make a discovery library that exactly fits your samples.
Thank you.
Can you say something about the implementation of dependent peptides in DIA?
Yeah, so at the moment it doesn't exist. So we were thinking about it, but so there's no implementation yet.
But it's likely to happen, or you think it's too complex to actually succeed?
Yeah, I think the concept will be quite different from the DDA concept. So it's I cannot say if we will do it, but would be interesting, of course.
So is it possible to combine libraries? Let's say that you've got a human cell infected with a pathogen, and you can generate the two libraries independently, or are you better off training a new discovery library based on some initial data using the two different genomes?
No, you can combine libraries. You just put multiple lines basically in the field where you are supposed to enter the library. You can also make sample specific. I mean, you can either combine libraries and use them all together with all of the DIA samples, and you can also make sample specific libraries if you want. So that you would do with having multiple protein groups in MaxQuant, multiple parameter groups in MaxQuant, and then each of the parameter group would get its own library.
Hi, my question is about libraries as well. Is it possible to create like hybrid libraries with DIA and DDA runs, experimental, I mean?
Yeah, not yet. So that's on the to-do list, so that one would actually export the intensities of the matches in the DIA library to a new library file. So not yet, but that's on the to-do list.
And do you have a comparison about these slides with the Spectronaut also? Have you compared?
No, but so in the paper like 2-3 weeks ago from Diane, they compared to Spectronaut, and so they say it's like twice as good as, I don't know which Spectronaut version they picked there, but so they say this is like twice as good as Spectronaut or something like this.
Okay. No, I saw that paper, but I didn't know that it was the last version of MaxQuant. So that was with the last version, with this one.
Yeah, so the paper only has a comparison to Spectronaut, right? So there's no MaxQuant, and there I don't remember which Spectronaut version they picked, but I only remember that it was twice as good or something like this. And since we are almost as good, then one can use transitivity, I guess, to infer that we are better than Spectronaut.
Okay.
Whatever was used there, I actually don't remember which version that was.
Okay. And last question, according to my experience, when I'm doing DIA with experimental libraries, I'm using Spectronaut, you get better results that in a discovery mode. The question is, why is here? So I feel that you would recommend to do discovery library with DIA Max. Why is it that?
Yeah, very good question. So. I mean, first of all, that's how they did the benchmark, and we didn't want to regenerate any like their data with other settings or something. So that's the easy answer. The more complex answer is probably that. So this recommendation that you can always use, or that the measured library is useless. So this only for Orbitrap data, and so at least when we look at the data, it looks like. There's actually more value in the measured collision cross-section than there's in the predicted collision cross-sections. Of course, it might again depend on the predictor that you're using, but at least to me, it looks like the prediction of collision cross-section is not really better than random prediction. But That's at least what we see if we use the available tools in our hands. And that's why there's a big value still in having the collision cross-section from the measured library.
Okay, last question. Yeah, one more. This is just to learn. You show when you want to, when you are talking about identification, you show, for example, precursors or I don't know, yeah, fragments and protein groups to compare which method is better. And have you have a look at the proteins, so average proteins? So what's happened if using different algorithms to do DIA, you detect like a lot of proteins, but not many protein groups. So which method would be better? So
these are protein groups, right? So I think looking at proteins instead is not really a good idea because so you're just getting the redundancy from the sequence database in. So that's why we always make comparisons on protein groups and not on proteins. So I would actually not recommend doing this with proteins because then you get a lot of arbitrariness into these comparisons, and I think that's not the way to do it. I would think, unless you have a very specific way of doing it in mind.
Okay, thank you.